Buonasera a tutti, sono Paolo Ravazzani, sono il direttore dell'Istituto di Elettronica e di Ingegneria dell'Informazione e delle Telecomunicazioni del Consiglio Nazionale delle Ricerche, nome abbastanza lungo. E anche questa sera siamo qui ad aprire un altro giovedì dell'Istituto. Ringrazio innanzitutto l'ingegner Clemente per la partecipazione, ma non faccio perdere altro tempo, avviso soltanto tutti i partecipanti che la seduta l'incontro sarà registrato e sarà poi pubblicato sulla pagina YouTube dell'Istituto. Non pongo altro tempo in mezzo, passo la parola a Giuseppe Virone che così potrà fare gli onori di casa al nostro ospite. Grazie a tutti e Beppe a te.
Grazie Paolo. It's a pleasure for me to welcome Antonio Clemente in this seminar, and because Antonio received this bachelor and master from the University of Siena, then he did the PhD in Grenoble with the University of Rennes, and from 2009 is involved in research in various positions, from research assistant to probably head of the group, if I'm not wrong, in CEA-LETI in Grenoble, France. Maybe this research center is really important for the telecommunication community, because they do really advanced research in this field. What I want to say that this seminar is also a preliminary and also a dissemination activity for several projects that we are carrying out in this period. And first of all, we are working in the resiliency plan, PNRR of Italy, and we have infrastructure projects, so big data, that is working on smart radio environments. We have other PNRR project called Restart, and we have two projects on that: smart radio environment for the spoke of Naples, and integrated terrestrial and non-terrestrial network for the spoke of Bari. And nonetheless, we also have forwarded this seminar to the consortium named Anterra. Anterra is a Marie Curie consortium, is a PhD network. And I'm really glad that many students of this consortium are here. So I don't just take any longer, and give the floor to Antonio. And of course, thanks for joining us for the webinar.
Okay, grazie Giuseppe. Thanks for the presentation. Thanks also for the invitation to this seminar. It's an honor for me to present our activities in this seminar. So we can start. Can you see the screen in full screen?
Yes, it is perfect, Antonio.
Perfect. So good afternoon, everybody. In this presentation, we will discuss a little bit on the control and manipulation of electromagnetic wave by using what we call programmable electromagnetic surfaces. So I'm Antonio Clemente. I'm working at LETI. LETI is the Laboratory of Electronics and Information Technology of the CEA, that is the French Atomic Commission. So the LETI is a laboratory that is based in Grenoble. You can see here in this picture the valley with the city, the Grenoble city, and a quarter almost of the surface of the city is taken by the LETI, this research center, by the CEA in reality. At LETI we are around 2,000 people. In the same, we call this la presqu'île scientifique in Grenoble. You have ST Microelectronics, Schneider Electronics, and you have the CEA, the CNRS, that is the CNR in France. And at LETI we are 2,000 people. You can see here several numbers. We are a research center that is a microelectronics research center. And our objective, we are in the middle between the academics and the industry. What we done is the industrial transfer of the technology that we developed in laboratory with academic partners. And at LETI you have 6 different departments, and I'm working in the department for system. Okay, our main activity is telecommunication, radar, defense, space application. And in my laboratory, in our laboratory, where I'm not the end of this laboratory, I'm not the chief of this laboratory, but I have a small research group with several postdoctoral fellows or PhD students. So in my laboratory, we are working on antenna measurement, electromagnetic channel characterization and modeling, design of antenna system. So, but now we can skip directly on the topic of this presentation. So we will talk about what we call today electromagnetic surfaces. You have different application of electromagnetic surfaces. You can use metamaterial cells or electromagnetic surface to control the impedance of a surface. For example, you can develop high impedance surfaces, such as this one. The objective of this kind of surface is to reduce the distance between an antenna and the ground plane in order to generate an in-phase wave. Other applications are the clocking, for example, electromagnetic clocking, frequency selective surfaces, or anomalous reflection and transmission. So in this presentation, we will see several applications of more on this part, but we can also consider these as frequency selective surfaces, where we have phase shifting in order to produce an anomalous reflection or an anomalous transmission. So when we use electromagnetic surfaces to do antennas, we can develop some spatially feeding based antenna technologies, such as reflect array or transmit array antennas. So today in the different research communities, we call this kind of antenna reflect array or transmit array, or also electromagnetic surfaces, RIS, reconfigurable intelligent surfaces, transmissive RIS, reflective RIS, reflect array metasurface, Huygens metasurfaces, metalenses. So there are different ways to call this kind of structure. The name sometimes comes from the model that we are considering to design this kind of structure, because we can consider these frequency selective surfaces or an array that works in transmission and reflection, or we can consider this a metasurface. Is depending from the particular model that we are using to design this kind of structure. So we will see a little bit later some models that can be used to do the design of transmit array antennas, for example. So basically, so here you have what we call reflect array antenna. Is an electromagnetic surface that operates in reflection modes. So we have a focal source similar to the case of a parabolic reflector. You have a focal element that illuminates this planar array, and by controlling the phase gradient on this flat surface, you can focus the beam in near or also in far field. And in the same way, you have the transmit array that is very close to a lens, is a flat lens, where you are working in transmission mode. Okay, the objective of this kind of antenna is to control the phase gradient. You can control it electronically, but you can also control it without electronic control. So in this case, for example, we control the phase gradient electronically on the transmit array surface, and we can focus the beam in a given direction. We can steer the beam in a given direction. So in some way, you can also focus, deflect the beam, focus the beam in near field. You can generate Bessel beam. You can generate orbital angular momentum beam. So you can manipulate the polarization. So looking a little bit on the state of the art, there are today a very big activity on this kind of structure. If we take a look on electronically configurable reflector array, what we can see is that today you have a demonstration up to 300 giga. In order to control the phase gradient on the reflector array surfaces, you can use different technologies such as liquid crystal, pin diodes, or also CMOS technologies. So this is a reflector array totally developed in CMOS technology. In the same way, for a reflector array, for a transmit array, sorry, in the literature you have a transmit array up to 300 gigahertz. There are different technologies that are used today to control the phase shift, the phase gradient on the surface, such as varactors, for example, pin diodes, MEMS, liquid crystal, and also in this case there is a transmit array that has been developed in CMOS technology, full CMOS technology at 300 giga. So in my research group, we are developing several transmit arrays or reflector arrays for different applications. Even in this case, we are working in the range between the X band around 10 giga up to 300 giga. For the moment, our reconfigurable technology works up to 50, 80 giga. And in higher frequency, we are developing fixed beam surfaces. So, but we are start also new project where we would like to develop electronically configurable transmit array and reflect array up to 300 giga. We will see this in the last part of the presentation. So, as I said before, there are different models for the simulation, for the design of this kind of structure. In this first model that I presented here, we are considering a transmit array or a reflect array that is a composition of several elements or unit cell in a flat surface, and we can consider the array theory. So the first point is we can model each element of the array by considering the Huygens principle. So in this way, we can consider that each unit cell of the array can be represented by two currents, a magnetic and an electrical current. And we have a transmission coefficient because in this case we are operating as a transmit array. So what we would like to do is to control the phase of each pixel of this surface, of this array, by giving a certain phase shift. And the objective of a transmit array is to, so we have a feed that illuminates this transmit array. This feed generates a spherical waveform. And we would like to compensate firstly this spherical wavefront by controlling the phase shift, the phase gradient on the surface. And after that, by electronically control this phase shift, we can steer the beam, we can focus the beam. So what we need to control is the transmission coefficient of this surface. In this case, in the case of a reflector array, we control the reflection coefficient. So now this kind of unit cell can be also simulated by considering electromagnetic full wave software, such as ANSYS electromagnetics, where we can consider periodic boundary condition and flocket illumination in order to simulate the unit cell. The unit cell is the pixel, the fundamental element of the surface. And we can simulate it by considering periodic boundary condition, because we would like to have the active radiation pattern, and we would like to extract the scattering matrix by considering that this unit cell is in a periodic structure or in a quasi-periodic structure. What is nice is that by considering this kind of model, we can also integrate the pin diodes, for example, the varactor diodes characteristics that we are using for the control of the phase shift of the phase shift electronically. The objective of the optimization of the unit cell is the maximization of the transmitted power and the control of the phase gradient. So now, what is interesting is that the unit cell can be also numerically modeled by considering this formulation that coming from the Huygens principle that I presented before. In this formula, you have different parameters, the epsilon parameter that can control the beam width of the radiation pattern that can be generated by this formula. What is interesting is this, by opportunely control the parameter epsilon, you can fit the simulation, the electromagnetic simulation achieved by considering the periodic boundary condition. So this is a quite good model to design numerically this kind of structure, this kind of unit cell. Unit cell is the single element of the antenna. So what I presented here are two different kind of unit cell. The first one, we can call it antenna, filter antenna. So you have an antenna that acts to receive the power coming from the focal sources, that is connected to a second antenna that will transmit this power in the free space, is connected by a bias, a metallized bias that is here. This structure can be realized on a printed circuit board technology or else on quartz or other kind of technologies. And in the other case, you have a structure that is very close to a frequency selective surface structure. So in this case, you have an anisotropic unit cell. Why this unit cell is anisotropic? As you can see here, you have two layers on the top and bottom that are two polarizer grid. So this unit cell can control the transmission phase, can select the frequency of operation where we can transmit efficiently the power from one side to the other one, and at the same time can change the polarization. So we will receive for example, a vertical polarization, and we will transmit with an horizontal polarization. We can rotate the polarization of 90 degrees. We can manipulate the polarization in this case. But you can do the same with this kind of unit cell. Only by rotating the top patch of a certain angle, you can generate a transmission with a certain angle of polarization or rotation. In some case, you can also generate a circular polarization by opportunity design. You can have a circular. You can achieve a circular polarization starting from a linear polarization. What we will see this later also. So in order to simulate this kind of structure, right, as I said before, we can use the array model. So this is a surface that is a discrete surface in a 2D grids, where you need to know the pattern of the unit cell that is generated in transmission. We know the array factor. We know the position of the unit cell in the array. What we need to know is also the impinging field coming from the focal source or coming, in the case of a RIS, from the free space. And what we would like to optimize is the amplitude and phase coefficient associated to each element. So what is nice is that this kind of formula can be also write as a quadratic form. This formulation can be easily used, for example, in a convex optimization problem, where we would like to optimize the amplitude and phase of or only the phase, because can be write also as a phase only problem, where we would like to optimize the phase of each element of the array in order to generate a specific radiation pattern, and we can also add constraint on this radiation pattern. What is interesting is also that this kind of formulation can be used to focus the beam in near field by using, for example, the conjugate phase approach. But we can also, in this case, use other approach, iterative procedure, for example, to focus the beam in near field. So, as I said before, the structure that I present, the model can be write as a quadratic form and can be used in a specific algorithm, for example, by using CVX toolbox, to generate an iterative optimization and solve a convex subproblem. So, as I said before, why we would like to, why we use convex optimization, because sometimes we need to respect some radiation mask, and we can impose constraint on radiation pattern by considering the convex formulation. And we can also, as I said before, focus the beam in near field. Now we can, by considering this theory, we developed several prototypes, and I will start to present different prototyping that we developed in the last year. For example, here you have a dual band, dual polarized transmit array that operate in a key band. So this kind of transmit array can be used, for example, for SATCOM communication. So for this reason, we operate in the key band that is around 90 giga, and in the K band that is around 29 giga. What is interesting is that with this kind of transmit array, we can generate a single panel that cover both frequency band. So as you can see here, you have two different focal sources, one for each frequency band. And on this surface, we generate two different frequency shift, we generate two different phase shift, phase gradient distribution, one to compensate at downlink. The downlink is the lower frequency band, and one to generate a beam, a focus beam in the uplink, that is the higher frequency band. So what is interesting is also that we can move the surface mechanically with respect to the focal source, and we can generate a mechanically the beam steering, as you can see here. For example, here we steer the beam mechanically at 20 degrees for each frequency band. You can see here the frequency response, the peak gain is here as a function, is the yellow part as a function of the frequency. And what is interesting is that the measurement fit very well the theoretical simulation that we achieved with the model that I presented before. Another possibility to do a model of this kind of structure is very close to the case of a frequency selective surface, where we can use the transfer matrix method, and we can do a cascade model of different admittance. For example, if you have a unit cell that is composed of three different metal layers, such as in this case, so you have two metal layers that are the polarizer. We can model these two layers, and after we can consider the blue layer as a layer where the admittance should be optimized in order to maximize the transmission coefficient from one side to the other one, at the same time control the phase shift of this transmission coefficient. What is interesting is that we can write this formulation as a combination of different transmission matrix. And by considering this simple formula, we can also retrieve the locus where we can achieve with this kind of structure ideal transmission coefficient without any loss, and we can cover the full, so that is this black ellipse that you can see here, and we can cover with 360 degree the phase shift. So this locus corresponds to this condition, and we can have 360 degrees of phase coverage. Now, we can also model this kind of structure with a disk equivalent model where we are considering the two flocket modes that the two flocket modes at least that illuminate this frequency selective surface, and the objective is to optimize the blue line, the blue level here, by considering an opportune design of this layer, so it's a rotator. And by considering this kind of structure, we can generate a transmit array that that can focus the beam. How we can do this? So another important behavior of this kind of structure is that by considering, for example, if we rotate this structure of 90 degrees, we can cover the same ellipse, but with a phase shift on 180 degrees. So I will explain you a little bit later this. So the idea is that by considering 4 different rotators, so each rotator corresponds to a specific phase level with a specific transmission coefficient. And by considering this, we can generate, for example, 45 degrees of phase shift, a relative phase shift between each rotator. In this way, we can after fix the layout of our lens with a specific phase gradient. What is interesting is that we can rotate of 90 degrees each one of these rotators in order to generate 180 degrees of phase shift, relative phase shift, and in this way we can generate 8 different unit cells with a 45 relative phase shifter. In this case, it's a 3 bits phase shifter. So you can see here that we can mirror only one of these in order to generate 8 different states with almost 45 degrees of phase shifter, of relative phase shifter. So this kind of structure can be used to design a transmit array, for example, a 300 giga in this case, where the objective was to achieve the highest gain as possible by considering standard PCB technology. So all this structure, the picture that you can see here is the transmit array that we realized and has been achieved in standard PCB technology. And also in this case, you can see the frequency response, the peak gain as a function of the frequency. You have the simulation, the measurement, and the ideal transmit array behavior. And what you can see here is that we are very close to the ideal transmit array behavior. We have not a lot of loss, with an aperture efficiency that is close to 30–40%. And here you can see the radiation pattern that we measured of this kind of structure. It's a very narrow beam, less than 1 degree. So now we can move on another part of this presentation, where we will talk about electronical reconfigurable unit cells. So what we presented before are only fixed beam transmit array antennas. This kind of structure can be used, for example, to develop some backhaul for telecommunication, or also to have short link communication with very high speed data rate. We will see this later also, an example of this kind of application. But what is interesting is the electromagnetic surfaces, as I said before, can be on an electromagnetic surface. We can implement the control of the phase shift, for example, by introducing pin diodes. So what you can see here are 3 different unit cells that we developed in the past. So the first 2 are unit cells that can be used to develop transmit array antenna. The last one is a unit cell that can be used to develop a reflect array antenna. For each of the 3 unit cells, you have pin diodes to control the phase shift on each element. So on the first unit cell, that is a binary unit cell, 1 bit of phase resolution, you have 2 pin diodes, and by opportunely control the 2 pin diodes, you can generate 0 or 180 degrees of transmission phase shift. In this case, we are talking about a binary unit cell with a 1 bit of phase resolution. This unit cell is developed on a 4 metal layers PCB technology, where you have 2 radiation elements on the bottom and on the top, a ground plane, and in the middle you have also the line that we use to control the pin diode state. In the second case, you have a unit cell that is a 2-bit unit cell. This kind of unit cell can be used to generate a 2-bit transmit array, but at the same time can be used to do a reflect array that operates with a 1-bit. So because we have 4 different pin diodes, 2 on the top layer and 2 on the bottom layer, by opportunity control the pin diodes, we can generate 6 different states, stay for the 2-bit transmit array or for the 1-bit reflect array. And by considering only a part of this unit cell, as in this case, we can generate a 1-bit reflect array element with 2 pin diodes. So, for example, by considering the last unit cell that I presented, we can optimize the phase gradient on the reflect array surface. Here you have 20 by 20 elements. For each element, the red and the blue colors indicate a unit cell that is in the 0 phase state or in the 180 degrees phase state. These different phase states are achieved by controlling the pin diodes. So the control of pin diodes is achieved by considering this bias line, and we apply on this bias line a positive or a negative current. So by controlling this, by switching this current between positive or negative level, we can control the 2 pin diodes in opposite state. One is on and the other one is off. By changing the current, we can change the on and the off state. So in this way, what we can do is we can control the surface current on the patch antenna that is here, and we can rotate the current, and we can generate a 180 degree of phase shift. So what is interesting is this kind of unit cell that I presented before can be used to generate reflect array, but also to generate transmit array. And in the past, we have several demonstrations of this kind of antenna. And as you can see here, you have all the reference of the different prototype. And as you can see, we can steer the beam electronically, and we can also generate circular polarization. And we can also switch between left-handed circular polarization and right-handed circular polarization. So I will show more details later about this prototype. So this kind of prototype can be used, this kind of transmit array can be used to generate an antenna for the future satellite constellation, for example. That can be an alternative solution to the mechanical steering antenna or to the active phased array antenna. So by considering an important properties of this kind of transmit array is that, as I presented before, we can illuminate this transmit array with a linear polarization, for example, and we can generate a circular polarization, and we can also control the rotation of this circular polarization. How we can do this? So by considering a specific distribution of H and horizontal and vertical polarized unit cell, as in this case, we can apply a phase shift, a 2-bit phase shift control, and by adding this specific vertical and horizontal distribution of the unit cell that is fixed, is not controllable. What we control is the phase shift. By using both function, we can steer the beam, and at the same time we can control the circular polarization. So what is important is that in order to avoid grating lobes, we use a random distribution of vertical and horizontal polarized unit cell. Why I say this? Because if we consider a fixed grid of horizontal and vertical polarized unit cell, as in this case, and we apply a 2 bits of phase quantization to steer the beam, to focus the beam, what we can see is that we will have a grating lobe in the cross polarization. So because you have, for example, when you steer the beam at 45 degrees, this is a polar plot of the radiation pattern that we can generate with this kind of surface. So here we ask to our surface to generate a beam in the cut plane 45 degrees, that is a diagonal cut plane, in a specific angle. But when we would like to generate this kind of beam, by considering this 2-bit phase distribution, what we achieve is a grating lobe in the cross-polar level. Now, to avoid this grating lobe, we can use this random distribution of unit cell, and as you can see here, we have no grating lobe. You have only one beam in one polarization, and you delete the grating lobe. Now, by switching this kind of by controlling this kind of phase gradient, we can steer the beam and at the same time generate dual circular polarization, switch the circular polarization. To demonstrate this concept, we developed this antenna that is a 24 by 24 transmit array antenna with 2304 pin diodes integrated on the surface. This transmit array is illuminated by a standard gain horn, and we demonstrate a 2-dimensional beam steering and the possibility to generate a circular polarization that is switchable. So what is interesting is that this kind of surface can be used with a quite low power consumption. By considering a bias current of 5 milliampere, in order to control the beam on this surface, we need 14.4 watts. Now, what we demonstrate, we demonstrate that we can steer the beam, and we compare the simulation and the measurement. Also, in this case, the simulation have been achieved by considering our tool, our numerical tool that has been developed in MATLAB. So another important application for the transmit array antenna is in order to develop a specific short link. For example, in D-band, the D-band is the frequency band around 140 giga. And we can develop a full system. What we've done in the past is the development of a full system with an integrated transceiver. Why we would like to use transmit array? Because in this case, we have only a single transceiver excitation. If compared to the case of a phased array, we can achieve wideband operation by considering low-cost fabrication process, only PCB. What are the problems of this kind of structure? Is that sometimes the space between the focal part and the flat lens can be big, but we can use specific techniques in order to reduce this kind of profile. And the other point that we are working on is how we can generate the beam steering at this frequency band. So here you have the system that we demonstrate recently. So you have a first PCB, that is this one, where you have an antenna in package module with an integrated transceiver. You have a duplexer, and you have an array of 4 patches that illuminate a flat lens. So the flat lens will generate the beam with high gain. The objective is this. So to generate these flat lens, we use a very similar unit cell to the one that I presented before at 300 giga. That is a frequency selective surface based unit cell. In this case, we generate, also in this case, we generate 8 unit cell with a 3-bit of phase resolution. And as you can see, the unit cell operated on a very wide band with very low losses in transmission that are lower than 0.8 dB, and the relative frequency band is around 40%. So we developed this kind of structure, we developed the full system, and we made the measurement. Here you can see the active measurement. Why I talk about active measurement? Because this is the ERP that we measured with the transceiver. So you have a power amplifier, and you have the transmit array gain. In this case, for this reason, we are talking about ERP. This kind of transmit array and system can be used to generate a specific point-to-point link, as you can see here. And what we demonstrate is the possibility to achieve 84.48 gigabit per second by using a 64 comm modulation. And the RX is located at 20 centimeters away from the transmitter. The power consumption is 600 milliwatt. So basically we have 7.1 picojoule for bits. Sorry. So the transceiver has been developed by considering the 45 nanometer CMOS technology. And all this work has been developed at LETI. So now the next step, as I presented before, this transmit array is a fixed beam. We can generate only a beam. We cannot control the beam electronically. So in order to solve this problem, we are working on the TerraMeta project, that is an European project, where we would like to develop transmit array that are steerable at 140 giga, but also at 300 giga. And we would like also to develop reflect array or reflective RIS to electronically also control the characteristics of the scattering of the multipath. So this is a project that started in this year, in the beginning of 2023. Now, a possibility to generate an electronical or reconfigurable transmit array in D band is by using what we call phase change material based switch. In order to do this, we develop a specific clean room fabrication process that is based on quartz substrate, and on top of that we can add specific material that has the phase change material. An example of this material is germanium telluride, and by heating this kind of material that can be integrated on this stack up, by heating this kind of material, we can control the we can generate a switch, a radio frequency switch. By controlling this radio frequency switch, we can generate a 1-bit unit cell, similar to the case that I presented before with pin diodes, that can operate on a very wide band and can generate a 1 bit of phase control. So here you have 2 bits, 1 bit of phase control on the full frequency band. So for the moment, we have not yet a demonstrator of this kind of array, but we done numerical simulation, and we simulate the full structure in HFSS by considering also the specific switch. And as you can see here, for 2 different beams, we have a quite good agreement between numerical simulation and HFSS. Next step will be the demonstration of this kind of structure. But we are working also on the development of specific structure in CMOS technology. So another application of this kind of surfaces has been demonstrated in the project, in the ACTRACT project that was called PrimeLock, in collaboration with the University of Bologna and CNR, with Professor Davide Dardari, Dr. Francesco Guidi, Anna Guerra, and also several different PhD students, where we used a transmit array in order to demonstrate a millimeter wave personal radar, or a millimeter wave radar for the mapping of the environment. So here you can see the specific setup that we used to do a measurement of the electromagnetic characteristics of the environment. And by using specific algorithm, we can generate the equivalent, the mapping of the environment. The transmit array that we used is the transmit array that I presented, one of the transmit array that I presented before, that is this one. It's an electronical reconfigurable transmit array that operates in key band that can generate electronical steering by considering a 1 bit of phase resolution with 2-pin diodes. So the same transmit array has been used in another European project, that is the RISE 6G project, where in collaboration with the French company Greener Wave, we done the first electromagnetic channel characterization by using multiple RIS. We use a transmit array to emulate a base station where we can generate electronical beam control, and you have a RIS, that is the reflector array of the company Greener Wave, that can control the feeding, the multipath, that can it can control the multipath feeding electronically. So what we done, we done several measurements. So here I would like only to show you one particular case. If we see, so in this case you have the transmit array that illuminates the RIS, the reflector array, and you have a user that is this monopole antenna here that emulates the presence of a specific user. So the transmit array illuminates the RIS. And you have two different cases. The case where the RIS is off and the case where the RIS is on. If we take a look, the frequency response, you cannot see difference between the on and the off of the RIS. But if you analyze these by considering specific Fourier analysis, Fourier transform based algorithm, you can have the phase delay profile, as in this case. And what you can see is that when the RIS is on, we have another contribution that is not present when the RIS is off. So here you can clearly see the impact of the RIS. So you have this first contribution is the direct link between the transmitter and the user. That is a side lobe between the radiation pattern of the RIS and the user. When the RIS is off, you have no contribution of the RIS to the PDD, to the PDP. But when the RIS is on, you can see an additional contribution that is the response of the RIS. So thanks a lot for the attention, and I would like also to thank the different collaborators from CEA, but also from external university research center. Only to conclude, we have a lot of open position in our laboratory. So if you are interested to this position, you can send me an email. Thanks a lot for the attention.
Thank you very much, Antonio, for the very nice presentation, very complete. Thank you. I have many questions, but because the presentation gave a lot of, I mean, it's really theoretical, but also with measurements and with prototypes. So it really can raise a lot of possibilities, a lot of questions. But first of all, I want to the audience, I want to encourage the audience to have some questions. So if anybody want to put the question in the chat or raise the hand. Okay. So first we have Caterina Frezza. So please, you can just speak up and yes, you can make your question. Sorry, no, you're muted. Sorry, you're not Caterina. Sorry, but sorry, you're muted. You're muted.
Caterina is my daughter because we don't use Teams. And my name is Fabrizio Frezza. I am a professor of electromagnetics at La Sapienza University of Rome. I actually am showing this webinar to some students of mine in my advanced electromagnetics course. So also in behalf of my students, I would like to ask you some comments about the assumption in the simulation of periodic boundary conditions in comparison with the real structures which are instead finite size.
Yeah, so I will reopen the presentation. Only one moment. So this is a good question. This kind of structure is a quasi-periodic structure in reality, and is a finite structure. But what we can see from when we compare measurement and simulation, here we use a simple model without by considering that you have a full periodicity for each unit cell. And as you can see, the agreement between the theoretical model and the measurement is very good. So what I would like to see is that, for me, it depends from the particular structure that you are using, such with unit cell. Sometimes in our simulation, so you need to study the unit cell in order to understand this. When you design the unit cell, you need to study the unit cell in normal incident, but also in oblique incidence, and check what is the performance of the unit cell. And another point is that you need to study the unit cell in full periodic boundary condition, but also in quasi-periodic. And you can see that there are some, it depends from the structure for me. Sometimes you can use only a simple periodic boundary condition for each unit cell. And sometimes if your unit cell is not totally symmetric, and when I talk about not totally symmetric, is that there are some structures that can generate a coupling that is not constant for each phase state. And in this case, you cannot use the assumption of full periodic boundary condition, but you need to design a subarray. But you can consider that your antenna is a quasi-periodic with a subarray.
For example, in the last slides, almost last, you mentioned a structure for which you do not have so far measurements available. So you performed only simulations. Did you try for such structure to consider what happens when increasing the number of cells considered? And moreover, apart from the border effects due to the finite size, there might be also some reflections because of the finite size. They are printed structures. So yeah, if you could give some comments on this.
So in our model, we consider the scattering matrix of the unit cell that is generated by full wave simulation. We consider the S11 parameter, but also the S21 parameter, in order to take into account the full link budget. So in order to discuss a little bit more, we can see the So in this unit cell, so as you can see, for each phase state, we have a different rotator. So basically, it's not a real periodic structure, because the rotator in the inner layer is not the same at each time. But basically, the radiation pattern that is generated by each of these rotator is very close one to each other. For this reason, the assumption that we have in periodic boundary condition for the radiation pattern is acceptable. In the other side, yeah, we use the scattering matrix that we generate in periodic boundary condition. And as you can see, the simulation, that is the numerical simulation, and the measurement are very close one to each other. So for this reason, we think that there is not a big impact of the quasi-periodicity. And another point, this is a quite big structure, because we generate, in terms of lambda, if I remember well, I don't remember well, it's 40 lambda or 60 lambda by 60 lambda, something like this, to achieve 45 dBi of gain. And we made only the assumption that this structure is periodic. For me, there are some structures where, for me, in the past, I have not example here, but we have a paper that we done with one of my PhD students in 2015 or 2016. Is a paper from Luca Di Palma, is the main author, the first author, where we presented exactly this. There are some cases where you need to consider a local periodicity. So if you're interested, I can send you this paper to show you in which case the periodic boundary condition can be not used.
Thank you.
And there are another point is that sometimes, as a function of the unit cell, you need also to consider non-normal incidence in the same model. You can consider the scattering matrix calculated, computed in the real incident angle. Okay.
Thanks, Antonio. I think there was a question from Dijon Lin, but probably now you just lowered the hand. So, but I think I saw the hand, so you can make your question, please. Don't be ashamed.
I'm not sure if you can hear me, because I said
no
microphone.
We can hear you. We can hear you.
We can hear you. Yeah.
Okay, that's fantastic. So maybe this question was already asked just now, but I was wondering. So from a transmitter array point of view, right? So you have some kind of feeder, and you use that feeder to excite the unit cells which is present in this transmitter array, right?
Yeah.
And you basically said, well, like you use a 3D simulation to model for the S11 and the S21 parameters, because you take into account the incident wave angle, right? Which is quite important, because it affects how efficient that cell is, I guess. But what I was wondering, because do you also focus also take into account, for example, like the coupling in between the cells? Because I could imagine that if the cell like receives some kind of like RF signal and re-emits itself on the other side, let's say from the transmitter array point of view, it will act something like the planar array, right? Which would mean that it has, I would assume, as an embedded release pattern.
So the first you have a different question from me in the same question. So the first one is the coupling, the mutual coupling between the unit cell. In order to take into account, is exactly the same. The question, the first question, that is, in periodic boundary condition, we are assuming that each unit cell has the same mutual coupling. Okay, we try to extract in a full periodic array the characteristic, the radiation pattern of the unit cell and the scattering matrix. So in this case, this is a kind of active radiation pattern. Okay, in this case, you can have a kind of mutual coupling impact. even if it's not the real one, because you are in a quasi-periodic structure in reality. But what we can see is that the periodic structure, the periodic assumption works as a function of the specific unit cell that you are studying. So the second question was more about the illumination, no, on the transmit array, no?
Yeah.
So it's a good question. When you are using our these electromagnetic surfaces as a reflector, a transmit array, you have a focal point, a focal source that illuminates this kind of structure. So in this case, you are working you have not an uniform illumination of the surface, but you have a certain taper that is generated, a certain illumination taper that is generated by your focal source. In the optimization, we take into account this taper because we consider the structure that is illuminating. So now there are different models to do this, this analysis. If you are in the Fresnel zone, you have not a lot of coupling between the one part and the other one, okay? But sometimes we are working, for example, in order to generate a low profile structure, we are working with a near field illumination. In this case, you need to design the illuminator at the same time than the unit cell. You can almost consider that you have a big cell that is the element that illuminates plus the unit cell, to take into account the coupling between the focal structure and lens. Is it clear? For example, even this, you have, for example, in the literature, some publication from the group of Professor Shonam in Toronto, where you have a leaky wave antenna that illuminates the transmit array with a distance between the two antennas that is lower than lambda. This is a nice paper. If you would like to see, to have more information about this question.
Oh yeah, please, if you can.
It's Professor Am, H-U-M. University of Toronto is leaky wave lens, something like if you put the leaky wave lens, you will retrieve the paper.
Okay. Yeah. Thanks so much.
You're welcome.
Thank you. We had Professor Nepa, but probably he left. So we go to the next one, and Simone Genovesi. Please.
Yeah. So good afternoon. My name is Simone Genovesi, and as Paolo, I'm from University of Pisa. Thank you, Antonio, for the very interesting presentation. My question is about the biasing lines that you use for controlling the diodes in the transmitter. I was wondering if you have seen any troubles, or if you are using just one polarization and the biasing line are in the orthogonal direction. I was just curious about that.
Yeah, I will take the slide. So this is a good question also. So you need to do the design of the unit cell by considering the bias line. As you can see here, in the bias line, you have some part. So this is we design a specific circuit on the line in order to isolate the DC and the radio frequency signal. If you see on this line, you have this kind of capacitance. And here you have a lambda/4 transformer. And we use this kind of structure to isolate the DC and the RF. Another point is that we do the simulation with one lines, but also you can imagine that when you have a big array, as you can see here, can you see here? This is all the bias line that you have. We do the simulation of the unit cell in the different condition of bias, and we try to optimize the performance of the unit cell in order to minimize the impact of this line. But you are right. In a lot of we try to generate to put the line in the cross polar, but you have also some coupler contribution. So here the dispatch is vertical polarized. You can see that you have some element of the line that is vertical. So you cannot put the line only in the cross polar position. Is it clear?
Yeah, thank you, thank you.
You're welcome. So you need to isolate it. I need to design the unit cell with the lines.
Thanks, Anto. I have probably a quick question. So you mentioned a material that you hit, I mean, at very high frequency to make it, let's say, reconfigurable.
Yeah.
So which is the heating mechanism? With light, with other RF?
Yeah, we are trying to different solution. If you take a look in the state of the art, you have laser on the top of this kind of phase change material. But the laser is bulky, basically. I have results where we are trying to implement lines to hit by current, but you need a very high level of current. But it's only, this is a bistable material, it's a non-volatile. So you need only to put punctually only a pulse, and after you can delete the bias, and you will maintain the state. The problem, so linked to the question from the Genovese question just before, 140 giga, the impact, if we put a current line, the impact is not as in the case of the 28 giga. So you have a lot of interference. For this reason, we are trying to do a mix between current or laser. But I can, we have some patent now ongoing. I cannot show you a lot of details on this.
Okay,
I hope
thank you.
Next year, maybe.
So it is a bistatic material, but of course it has different local properties.
So what we, only one moment. So you can consider that the unit cell that we develop with phase change material is very close to this one. So the difference is that here you have pin diodes that are in package.
So it's not a continuous material. Okay, okay.
We delete the pin diodes and we put locally some micron square of germanium telluride. Okay, and on the top of this you have silica, you have diox, you have a SCO2 or SCO2 or other kind of diox. What is interesting is that when you hit with a specific pulse this material locally, so what you can do is to have two different current line. Okay, if you hit locally this material with a current pulse, you will switch between a resistive or not condition. Okay, and by considering this, you can have a switch similar to the pin diodes.
Thank you. Okay, yeah, it's very interesting because with the pulse, I mean, it doesn't drain power when it is in static mode. So it just absorb power when it is switching. So this is really an important improvement.
Yeah, we done a study in a paper where we compare the power consumption, but not locally, not only in one instant, but in a 1 year of utilization of the antenna, and you reduce drastically the power consumption. Yeah. Even if locally is very high, you have a very big peak, but after that you can you have no continuous power.
Yeah, thank you.
But the problem of this kind of material is that the time switch It's not the same than pin diodes. For a pin diodes, you can switch with nanosecond. On a phase change material today is in the order of millisecond.
Okay. Okay.
It's not the same application.
Okay.
For the moment. You're welcome.
Thank you very much. So, is any other question from the audience? Okay. So probably. So in this case, I can thank also the audience for staying so long, because it was a very also intense session of Q&A, very interesting. We had professors, students, researchers, a lot of different also let's say level of the scientific profession. So it was very good. And of course, thanks again to Antonio for giving this talk which really highlight the relevance of his research at CEA-LETI. So I think with this we can close this seminar, and stay tuned for the next edition, or for the next talks that are going to be on this channel. Ok. Lucano, vuoi dire qualcosa?
No, siamo a posto.
Okay. Okay.
Thank you very much to the speaker. Very nice and interesting contribution.
Thank you very much.
Thank you very much.
Thank you very much.
Bye.
Bye.
Thank you.
Thank you. Goodbye.
Goodbye.